In lecture 24, we are basically going to consider second-order circuits. Second-order circuits is a circuit that has two storage elements. If you follow the first-order circuits, you essentially you will understand fairly easily how to deal with second-order circuit because the process will be the same. We are dealing with two storage elements, that is either an inductor and a capacitor typically, or two inductors or two capacitors, although there are cases where that can lead to a first-order circuit if you can combine them into one. But by and large, let's assume that a second-order circuit is one that has two storage elements. Okay. So what is the objective of this mini lecture 24? In this mini lecture 24, we want to essentially revisit nodal and mesh, much like we did for first-order circuit, but bringing in now two storage elements into nodal or mesh. And when we do that, you are going to see that we are going to end up with a second-order differential equation, which is a significant part that's different here compared to the method. The analysis method, that is the nodal and mesh, is fairly similar to what we did in first order, but we're going to end up with the second order differential equations, and we're going to have to revisit that, something that the content that you saw in your differential equation course. The solution to those is much more complex. We're going to have two initial conditions and so forth. So first major objective is to relook at how to do nodal or mesh with two storage elements leading to a differential equation of the second order. Again, we're dealing with circuit with switches that have DC sources. And then we're going to spend a little bit of time in this lecture talking about how do we solve differential equation of the type that we're going to see in this particular segment here. Okay, so let's go with some notes here. We are solving, let me just get my pointer here. We are solving second order circuits, which means two storage elements. And again, you can kind of extrapolate, that's going to give you second order differential equations. So we have second order circuits, generally circuits that have DC sources, but with switches. So the switch is moving, whether the switch is opening or closing, it's what causing a change in the circuit. Other than that, the circuit have DC sources. So as you know from first order circuit, we solve these circuits before the switch move, and we solve after the switch move. So we usually have separate circuit. If you have one switch motion, you have two circuits, one before, one after. And that's typical what we do. The first time period, because the circuit is a DC circuit, it has constant sources. The first time period is typically the capacitor looks like an open circuit, because if everything is constant, the capacitor current is zero. So we model the capacitor when it sits in everything is constant as an open circuit, broken wires. And the inductor behave like a short circuit, a wire, when everything is constant for a very, very, very long time. So those are the kind of things that we've seen before. Of course, we didn't see them together in the first order. We saw them separately. Finally, regardless of what you're being asked in a problem, the capacitor voltage and the inductor current are the initial conditions. So you must calculate those two because that's what we're going to use for initial conditions in the circuit. So hint, second order circuits, you're going to need two initial conditions. Okay, so I want to start by talking a little bit about nodal and mesh. We've been speaking about nodal and mesh for a long time, but I just want to relook at nodal and mesh in the context of a second order circuit. I want to write it down so that makes sure, and then we'll do an example that's going to lead us to a discussion on how to solve a second order differential equation. So here we're talking about nodal analysis, and just so we be clear, again, the first time period before the switch move, it's typically a simple circuit. The capacitor is not there, the inductor is not there. So when I speak to nodal analysis, I'm really speaking after the switch move and the capacitor and or the inductor are present in the circuit. So we prepare the circuit. What do we mean by prepare the circuit? We essentially identify all nodes. Be careful at not missing node always. We select a reference node. We label the other nodes and we insert current on each resistor, inductor, and capacitor. So often I would say we insert current on each passive element if none is present. If you have a voltage on some element, don't add another. If you have a current on some element, don't re-add another current and relabel it. Use the current that's there. And then so that particular part is really what we call preparing the circuit for solutions. Okay, we haven't written any equation. The first equation that I typically encourage students to write is what I call the source equation, which is really a KVL equation. Okay, in essence, essentially, we're writing for each voltage source, we write the voltage is equal to essentially the difference between the node potential should be equal to the value of the source. Those are easy equations to write. We write them for independent voltage source and we write them for dependent voltage sources. So these are easy equations to write. So I suggest we do. We form supernode when we have voltage sources. Okay. And in cases where supernodes are sharing a common node, we combine them. Okay, so that's kind of just some reminders about node analysis. Now, this particular page here has to do with only the mathematical formulation. Here, we do KCL, and I'm going to ask you to again do KCL in terms of currents, particularly with first and second order circuits. We do KCL at each regular node, and when I call regular node in the past is a node that is not the reference node and is not connected to a voltage source. So we do KCL at those nodes, and we do KCL at supernodes that do not have the reference nodes. So these are a set of KCL equations at either regular nodes or supernode. Then I want you to write Ohm's law for each resistor current, okay? That is current is equal to node voltages divided by resistance. We write Ohm's law for all of them. And then the next step is to use this Ohm's law into the KCL equations, okay? So we use this into the KCL equations here. So up to now, up to this point here, we haven't done anything with the inductor or the capacitor, okay? Then I want you to step aside and write the capacitor current voltage relationship, and I'm purposely saying current voltage relationship because the capacitor current is the capacitance and the derivative of the voltage. That's why I'm saying current voltage relationship in this case. I want you to step aside and write it. Don't write it generically. Don't write IC is C dV C dt. Write it for the current to the capacitor and the voltage across the capacitor, okay? So that it pertains to the circuit and to the solutions that you're doing. Then you do the same thing for the inductor. You write the inductor voltage current relationship because the inductor voltage is the inductance times the derivative of the current. We write that again, don't write generic equations. Then we bring the capacitor and the inductor relationships into the KCL after the Ohm's law equations, okay? So at this point here, I'm going to encourage you to look at how many unknowns, how many equations you have. If you have the same amount of unknown as the number of equations, then you can start using substitution to get one differential equation for the solution. We're going to practice this quite a bit, but I wanted to lay it out so that you can see it and you can refer to it basically back. Okay, and I'll try to use this outline in my solution to reinforce that. If we're doing mesh is a counterpart of nodal. Again, we prepare the circuit in mesh as well, but our preparation is identify the finite meshes, insert and label mesh currents in those finite meshes. Then we insert voltages on passive element resistor, inductor, and capacitor. If none is present. If you already have a voltage somewhere, don't insert another one, okay? All right, so, and then we do source equation, but the source equation essentially the source equation for mesh is for each current source. We write each current source in terms of the mesh currents, okay? So, because if you have a current source essentially on a branch, it forces the mesh current to be equal to that current source value. And then in the case when you have a current source shared by two meshes, you have to do a super mesh between the two adjacent meshes. So that's what we'll be doing KVL in that super mesh. All right. All right. So final set of instructions here. You do KVL in terms of voltages, just like I want you to do KCL in terms of current, and we do it at each mesh with no current source. So mesh with no current source and around super meshes. Okay, so two things. We have KCL at regular node and then super node. In mesh, we have KVL in mesh with no current source and around super meshes. Then we write Ohm's law for each resistor current, each resistor voltage. So what Ohm's law does essentially express the voltage on the resistor in terms of mesh currents. Then I want you to use this Ohm's law into the KVL. And thus far, again, at this point, we haven't touched the inductor and the capacitor. Then step aside, write the capacitor, again, current voltage relationship in terms of the labels that you have on your circuit. Do the same thing for the inductor voltage current relationship. And then at this point, you bring this relationship for the capacitor and the inductor into the KVL plus Ohm's law equations that you have. So I encourage you at this point to look at how many equations, how many are known, and if you have the right amount of equation for the right amount of unknown, then you begin using substitution to get the single differential equation for the circuit. Okay, so that's the process that we're going to do. And then I'm going to basically start with an example. I'm going to go on paper so that you see me doing, and I'm going to outline. I'm going to do an example with mesh. I'm going to outline the process here. And then we'll use that example to engage into how do we solve these differential equations during that. You know, before we go to the example, just to note that for this entire section, the second order circuits, we essentially going to, our solution, our nodal and mesh, is going to lead to a differential equation that looks like this. You're going to be very familiar with this. So and we're going to spend some time today discussing the types of solutions that we get. This is a differential equation that you've seen in your differential equation course. These parameters here, alpha and omega n, are constants. So this is the simplest form of second order differential equation. Everything is constant. And we're going to look at the case we're going to look at essentially. We're going to first consider what we call the source-free or zero input response, that is f of t is 0. And then later on, we look at cases, what happened when f of t is a constant. Again, we're looking at this differential equation. We're going to learn we're going to develop, for each circuit, we're going to have its own differential equation. We're going to do it using nodal and mesh. And I'm going to step aside and talk about what is the solution to that differential equation. Basically, a review of your differential equation content. Okay. So let us go into the document camera. Okay, and it's all focused, all good. So I put a problem here that's going to help me. And again, this is a problem that's as simple as it gets. I'm going to use this. I'm going to develop this problem using mesh. I decided not to do it using PowerPoint. I decided to do the process and highlight the steps that we just talked about in mesh so that you can see that. So the first thing that we have here, we have a switch here. The switch is closed. The switch is closed. That's what and then at t equals 0, it opens up. Okay. So at t equals 0, this switch opens up, disconnecting this battery that has a voltage V0 from the circuit right there. So as we know, we solve the circuit for t less than 0 and another for t greater than 0. All right. So anytime you see a switch, you basically solve before the switch action and after the switch action. And of course, for t less than 0, we have a circuit that have the resistor here, the inductor here, and the capacitor like this, and this is connected to my battery V0. Okay, with the voltage across the capacitor being VC. All right, so that's for t less than 0. So this is a circuit that has been like this, and this is a battery, so this is constant. It's been like this for a very, very long time. We now know that the circuit that really exists for t less than 0 is the inductor behave like a short, like a wire. The capacitor behave like an open. And of course, you have the battery across here. So this is the inductor here, and my voltage across my capacitor here for that, because everything is constant for a very, very long time. So we look at this as this is actually the circuit. The inductor really behaves like a wire. And then we're looking at here, we need the current also on the inductor because that's going to be our initial condition. Okay, so we need the capacitor voltage, but that was asked. But we also need the inductor current here. And these are fairly simple. The capacitor voltage, clearly VC at 0 is V naught. It's just parallel to that, parallel with the battery here. Okay, so that's V naught. And of course, the inductor current is minus V naught divided by R. So these are our initial condition. And I should put I at 0. These are our initial condition right there for T less than 0. Okay, so that gives us, so typically this is what we said, the first time period is a simple circuit. So when I talk about using mesh and nodal, mostly talking about once the switch has moved, okay, because the inductor and the capacitor are now going to wake up at T equals 0 because there's been a change in the circuit that forced them to behave like inductors and capacitor. For T less than 0, what you're doing essentially here is charging the inductor and the capacitor with a DC source. Right here. So now we're going to talk about what happened. So let's do separation here. Let's look at T greater than 0. So the procedures that we talked about, nodal and mesh, relate to that time period. So for T greater than 0 here, this switch open, disconnecting the battery. So what do we have here? We have a simple R, the inductor, and the capacitor. And of course, I'm going to use mesh analysis here. So I can basically have one mesh current, I. This is my voltage VC that I have. And I'm going to put voltage on the inductor and voltage on the resistor here. Let me put V1 on the inductor here and V2 on the resistor. So again, when we do mesh, we essentially prepare the circuit by identifying the finite mesh. I know this is a simple circuit. We have only one mesh, but still shows you the process here. So, and then we put voltages on our passive elements. If one doesn't exist, in the case that you have VC, we don't need to add another voltage. We already have the voltage on the capacitor. And when I mean voltage on the passive elements on each resistor, inductor, and capacitor, these are, we don't put voltages on sources. Okay, so this is kind of prepare the circuit for solution right there. All right, so no source equation, because no current source. No current sources here. Okay, so no source equations because we have currents, we have source equation when we have current source in mesh. We don't have any current sources, so no source equation here. So I'm going to go ahead again. I have only a single mesh. I'm going to go in KVL in mesh I. Okay, that's the process that I was describing here. So KVL in mesh I is what? Minus V2 plus V1 plus VC equals 0. So that's my KVL. Of course, if you had multiple mesh, you're going to have more than one KVL equations. In this case, I only have one mesh, so but it shows you the process that I was talking about when we outlined the mesh solutions. So those are all my KVL equations, just happen to be one. Okay. Then I do Ohm's law. Of course, I only have one resistor. I get that. So what is Ohm's law? Ohm's law is V2 is equal to minus R times I because the current is entering the negative terminal. So that's the minus. And then I'm going to again, so the next step here is KVL plus Ohm's law. Okay, in other words, I'm going to put my KVL and my Ohm's law into my KVL equation. If I had multiple Ohm's law, multiple equations, I would do them the same way. So what do we have here? We have R times I plus V1 plus VC equals 0. Okay, that's my KVL plus Ohm's law. So I'm specifically showing you these steps in kind of discrete so that you can see exactly how that maps into my outline for the mesh procedure that I did earlier. So now I write the capacitor and the inductor. For the capacitor, what do I have here for the capacitor? What is my current to the capacitor is I. I'm going to have I, and the capacitor basically has a capacitance C, by the way. I is C dVc dt. And then for the inductor, what do I have? I have V1 is equal to L di dt. Okay. So these are my, again, what do I have right now? I have this one equation here, and then I have 2 and 3. Okay. So if you look at there, you should essentially be able to see that I have 3 equations to unknown, three unknown. What are my unknown thus far? Again, I have I, V1, and VC. I, V1, and VC. Okay, so I have 3 equations, 3 unknown. So this is the part where I'm going to essentially use substitution to get my differential equation. Okay, going to use substitution to get my differential equation. So I'm going to, let me first use the inductor. We first use the inductor. So what do we have here? We have I plus L di dt plus Vc equals 0. So when I do that, I'm done with the inductor. I've used the inductor. I've used any place that I have V1, I've used essentially L di dt in my other 2 equations. Okay, then I'm going to use the capacitor equations into this. So wherever I have I, I'm going to put C dVc dt. So what do I have here? R times C dVc dt plus L ddt times C dVc dt plus Vc equals 0. You can see the differential equation coming right there. So I wanted to show you those without the PowerPoint features so that you can see me doing it, because that is the process that I want you. Admittedly, this is a one mesh problem, so it's, you know, as simple as it gets, but it shows you in detail the process. Okay, so let's multiply this thing through. What do we got here? RC dVc dt plus LC, second derivative with respect to Vc, plus Vc equal to 0. Okay. The last step we do, we normalize. And we will always normalize such that the highest derivative, which is the second derivative, has a unit coefficient. So in essence, I'm going to divide the whole equation here by LC so that the highest of the derivative has 1 as a coefficient. When I do that, what do I get? Second with respect to t squared for Vc plus R divided by L plus 1 over LC Vc equal to 0. That is my differential equation for this problem for t greater than 0. So a little bit of a recap here, you know, before, you know, I'm going to go back to the PowerPoint, but I think this was important to me that I do it on paper, that I don't skip any step, that you can see everything in one page. So let's do a little recap here, and then I'll go back. We're going to focus on how do we solve differential, dVc dt. We're going to, you know, again, I apologize, I forget this, the dVc dt part here. How do we solve differential equation of that nature? We're going to talk about that, but let's just recap a little bit here. We are solving second order circuit. That means there are 2 storage elements, and you can see the storage element. We're solving second order circuit that have DC sources and switches. In this case, there is one switch here. The switch is connected before t equals 0. It's just connect, and then it opens up at t equals 0. And it has a battery, so it's a constant battery, like a 9-volt, a 12-volt. I'm calling V0 here. So we solve this circuit for t less than 0, recognizing for t less than 0, the circuit has been constant for a very, very long time. So the capacitor behaves like an open and the inductor like a short. Whether or not I ask you to calculate the capacitor voltage or the inductor current, we need those 2 because they are the initial conditions for second order circuit. So we need the inductor current, and the capacitor voltage. So we did that. For t greater than 0, though, the switch motion, the switch changing, opening up, brings back the inductor and the capacitor because that created a change. All right. So now, obviously, once the switch open, it disconnects the battery from the capacitor. So we are clearly looking at a source-free circuit or zero input. Okay. So this is going to give us, obviously, an homogeneous differential equation because there is no source in that circuit. So you can expect the right-hand side to be 0, as we noted here. Okay. So the first thing I do, I prepare the circuit here in a typical mesh fashion. I identify my finite meshes. I put mesh currents in each mesh, each finite mesh. It's only one mesh. I get that. And then I put voltages on all my passive elements that don't have voltages. So the capacitor already had VC. I don't add another one. And I put a voltage plus and minus and label on the inductor and the resistor. Then do I write source equation here? In mesh, we write source equation for current sources. There is no current source, so no source equations here. It's only one mesh, so I do 1 kVL in mesh I minus V2 plus V1 plus VC equals 0. Then I go ahead and write Ohm's law for my resistors. What Ohm's law does in mesh, it converts the voltages to the mesh current. Okay. I use the Ohm's law into the KVL equations. That's the step. Again, that's why you're seeing the line. I'm showing you the various steps. And then I write the capacitor and the inductor relationship based on what I have in my circuit. Of course, this looks a little bit like a generic equation, but it's not. The current to the capacitor is I, and the capacitor voltage is VC. I make sure that I satisfy the passive sign convention when I write this relationship. Is the current entering the positive? Yes, it is. And then for the voltage for the inductor, the voltage is equal to the derivative of the current multiplied by the inductance. Then I bring them into, so I have these two equations and the KVL equation. So I have 3 equations, 3 unknown, and I'm going to basically use substitution to get down to 1 differential equation. The first thing I do, I use the inductor equations. And when I do that, anywhere that I have V1, so I have V1 only here, I basically put the inductor relationship. Okay. And then I bring in the capacitor after that. So anywhere I had anywhere that I have I essentially put it as CdVCdt. That's what you got here and here, which leads me to this. The last step here is to normalize such that the highest order derivative as a unit coefficient. And that's something we're going to do in a standard way when we discuss how to solve this differential equation. What's interesting about this, every single circuit would have its own differential equation. The reason that I didn't put any values in R, L, and C, because depending on the value of L, C, and R, it's going to have a different types of differential equations. So we're going to see that in the future. But every circuit typically will have its own differential equation that we come up with using mesh and nodal. So now what am I going to do? I'm going to essentially talk about how do we solve these types of differential equations. And that's going to be a fairly general conversation. Then I'll go back and solve this circuit. I'll put some numbers in R, L, and C, and then we solve for that solution. Okay, so give me a second here. I'm going to go back to the PowerPoint. So this will be the standard form of differential equation that we're going to solve. The only 2 cases we concern in this particular section here is the case where it's equal to 0 in the case of a source-free circuit. And later on, we're going to have essentially equal to a constant. Other than that, we're not doing the more advanced types of solutions, more sophisticated differential equation that you had seen in your differential equation course. So when you get a differential equation here, I'm going to ask you to identify the damping coefficient, which is that constant alpha. It's essentially the coefficient associated with this first order derivative divided by 2. Okay, so this assumes, again, we agree to normalize our differential equation so that the highest order derivative has 1 coefficient. Okay, so I'm going to ask you to identify alpha. And I'm going to essentially ask you to identify the, I should say, resonance/natural frequency, because in some cases they call it the natural frequency, not the resonant frequency. So that omega n. So basically, omega n is the square root of the constant that essentially is connected with VC in this particular case. So again, we're looking at an homogeneous differential equation. So the response is, we can call it the natural response. In your differential equation course, you call it the complementary response. So in electrical engineering, we call it the natural response of the circuit. Natural means without any external source. That's what we call it. So again, you are going to be asked to identify the damping coefficient alpha and the resonance/natural frequency. So let me go back to the example we were just doing here. I'm just going to toggle back and forth. So when I'm saying alpha, alpha comes from this value. So alpha would be R divided by L divided by 2. So that's alpha. That's a damping coefficient for this. And the natural/resonant frequency is going to be the square root of this. So that's because this term here is omega n squared. Okay. So you essentially, once we get the differential equation, I'm going to ask you to identify alpha, omega n, and then we proceed to the solution. So let's go back to the PowerPoint. So what we're going to do here is essentially straight out of your Math 45, your differential equation course. The textbook obviously does the same thing, but I wanted to do a review. We are not asking you to prove anything. We basically ask you, once you get the differential equation, you identify the damping coefficients, the resonant frequency, and then you write the solution depending on these values. And I'm going to show you there are 3 cases. If you remember much about your differential equation course, there are 3 cases. That's going to depend on the value, the relative value of alpha and omega n. Okay, so let's cover these 3 cases, and then I'll go back and put some value into my resistor inductor and do 1 case just to show you, and then we'll pick it back up. All right, so there are the 3 cases here. All right, the 3 cases have to do with the value of alpha and omega n. So what we are essentially saying, we're saying that depending on what's under the radical here is positive, it's negative, or it's 0. These are the 3 cases we're going to be dealing with. We're going to be dealing with, first, we're going to be dealing if it's positive. So we're going to have a basically square root of a positive number. Then we're going to be dealing if it's negative. So we have a square root of a negative number. We're going to pick up a complex value here. And then the last case is what I call a borderline case, is when alpha is equal to omega n. So what's under the radical is 0. We have what's called a double root. Okay, so this is, again, you can look at your differential equation course as a refresher. We're putting this as a summary in order for you to do that. So let's look at these 3 cases here. 3 cases occur. The first case is alpha is larger than omega n. So when you get alpha, I want you to look at alpha and omega n and tell me which case it is. This is what we call the overdamped case. Overdamped because it dies out very quick. Okay, it's very damped. So what's under the radical here is positive. So the square root is essentially, you get two, S1 and S2 are 2 real numbers. Okay, so you get 2 exponent, they're real, they're negative number, 2 exponent that's dying out. That's what you get here as a result of this case here. When what's under the radical is positive, you get 2 real values. S1 and S2 are real values, but they're negative. This is what we call the overdamped case. Again, we're going to cover this in examples over and over again, but let me just go back. I'm going to ask you to identify the damping coefficient, alpha, and the natural frequency, omega n. Okay? Once you identify this, I want you to compare the 2, which one is larger, and you identify the case that we're dealing with. The first case we're dealing with, again, is the case of the overdamped, when alpha is larger than the omega n, the natural resonant frequency. Okay, that's the overdamped case. This is the case when you turn off your computer and you hear that sound go, because it's essentially all the energy is dying out. That's the case you hear. Okay. The second case, it's actually a super interesting case. It's actually a practical case. Alpha is less than omega n. So you have what's under the radical is essentially a negative number. So you pick up 2 complex values. Okay, that's the complex J here that I'm introducing here. Okay, so S1 is minus alpha plus j times omega d. Omega d is the square root of omega n squared minus alpha squared. So j being the square root of minus 1. So S1 and S2 are complex numbers. They are also the conjugate of each other. In other words, their imaginary part have opposite sign. That's what conjugate means. Okay, so you are looking at two complex numbers here. And the solution is called the underdamped solution, underdamped case. And this is the solution we will be using. The second one we won't be using as much now. The solution is VC of t is e to the minus alpha t times a cosine omega dt plus b sine omega dt. Okay, you can see the complexity of the solution is becoming more so. All right. So here, A and B are going to be determined by initial conditions. All right, so that's case 2. Case 2 is probably the most interesting case in real practice. All right, case 3 is the least interesting. Case 3 is what we call a borderline case. You actually often have to tune the circuit to get case 3. When alpha is exactly equal to omega n, so what's under the radical is 0. We have what's called a double root. S1 and S2 are equal. And this is the solution for VC of t. And again, you've seen all this, but we're going to practice. This is what's called the critically damped case. This is not a case really that you see often. So this is the least interesting case for the two of us. 1 and 2 are the most common, 2 being the most interesting. Okay, so in the case of a double root, you see that t is being put there as for the double root there. Okay, so that's the form of the solution. Okay, so what I'm going to do now, I'm going to go back. I'm going to go back to my problem here. I'm going to put some values. Okay, I'm going to put some values, and then I'm going to say, okay, what case do we have? All right, so let me go back. Again, I've solved the problem on paper. I'm going to go back to the PowerPoint slide here, and I'm just going to put some values. I'm going to say, okay, let's look at that circuit we were solving that we just solved, all right, for t greater than 0. I put the initial condition on the inductor to be 2 amps, the capacitor voltage to be 1 volt, and then let's solve for I and VC, okay? So we essentially go back to that differential equations that I just showed you, all right, that we just came up on paper. So I'll just show you again on paper what we did so that you can kind of correlate with this. This is what we did on paper, that differential equation. So what I'm doing here is putting essentially some values for R, L, and C so that we have a case, because right now, how would we know a case if we don't have values? Okay, what case do I have? Am I case 1, case 2, or case 3? So I put some values, and I also put some initial condition values. And then we're going to see what case we have and what the solution looks like. Okay, so let's go back to this. So I put some value. Again, the resistance is 6 ohm, the inductor is 0.4 Henry, the capacitor is 0.2, and then the initial conditions, again, we put some initial condition. The current on the inductor initially is 2 amp and the capacitor voltage is 1 volt. All right. So again, what I expect you to do once you get the differential equation, you identify these two values, the damping coefficient and the natural/resonant frequency. It's essentially the coefficient as the damping coefficient is the coefficient associated with the second order derivative divided by 2. That's what you see is this thing divided by 2. So it's, in this case, it's 7.5. The natural/resonant frequency is the square root of that value associated with VC. So it's 3.53. What case do we have? We have the overdamped case. Alpha is larger than omega n. So I just want you to proceed and calculate the true value of S using the formula that we just showed you. Okay. So we're not asking you to prove, we're not asking you to go into any kind of high detail. We're asking you to recognize what differential equation you have, identify the case, and write the solution. So the solution for VC of t is given by this. Of course, we still have these two coefficients here, A and B, that are going to come up from because of initial conditions. Okay. So of course, once we find the voltage in this, we write the general solution for the voltage. We have to calculate the inductor current. Turns out the inductor current is also the capacitor current, so I can just differentiate the capacitor and multiply by C, the capacitor voltage, and multiply by C. So it takes some doing to do a derivative of the voltage here. You have to know how to do a derivative of the exponential function. So when you differentiate the exponential function, you get that minus 0.886 multiplied by A. So you're going to have to practice this. So here's a solution for the inductor current, and we have to multiply by the capacitance, which is 0.2. So now I have the capacitor voltage, the inductor current. I'm going to go ahead and apply initial conditions. I'm going to say VC at 0 is equal to 1 volt. So when I do that, when I set T equals 0 in both of the exponent will go to 1. So it's going to be 1 is equal to A plus B. And then I'm going to say I at T equals 0 is equal to, I believe, 2 amps. That was the initial condition. And then you're going to get Q is equal minus 0.177A minus 2.82B. And then we solve for A and B. So let me show you that. Okay, so I is equal to 2. So when we solve for A and B, we get these values. So this is the complete solution with the initial condition being enforced so that we calculate this constant. But this is the first time that you're seeing this in the circuit analysis context, although you've seen that in your math, in your differential equation. So we're going to look at more example. We're going to talk about this, but I wanted to give you a fairly detailed, essentially explanation to this. So let's recap before we close this particular lecture. Of course, this lecture is obviously very significant. We focus on doing mesh, on a one mesh circuit. Let me just quickly show you this. Again, we essentially focus on doing mesh. We look at a one mesh circuit. We got essentially a second order circuit with a switch that opens up. When the switch opens up, we get a source-free circuit here. Okay, so we had to calculate the initial conditions, which is the inductor current and the capacitor voltage. Okay, so we learn how to do a full mesh, even though it was a one mesh circuit, but it's a pretty comprehensive process here to get our differential equation here. Then we went back, let's go back to the, okay, so we went back here. Let me just quickly go back. We put some values so that we can have a case, one of the three cases that we're talking about here. We identify alpha, we identify omega n, okay? We identify we have an overdamped case, and we calculate those two roots, S1 and S2, and we write the general solution for VC. Once we write the general solution for VC, we also need the inductor current so that we can have the means to enforce initial condition on the capacitor voltage and the inductor current. And we do that here. And then we use initial conditions to get A and B from these two initial conditions. So we're going to stop here, let you take a breather, and then we're going to pick some example here using this concept. Of course, we'll do at least case 2. We'll do mostly case 1 and 2, the overdamp and the underdamp. The critically damp, probably not much because it's basically a rare case. Okay.